is three things. One, it's just a little puzzle proof that I'm going to show you. Two, it's a really handy tip for solving problems. And three, it's also a perfect example of a really clever proof technique called induction. Now with the video. Okay, so this guy called James Tanton has set this puzzle, and I solved it. So that's kind of cool. So I'm gonna explain it. Okay, so let's say you have 10 dots. Let's do dots. Now let's split them up. So you can split them up however you want to. So you can split 10 dots up into like 7 and 3, 5 and 7 and 3, 4 and 6, however you want. You decide. Mom, you decide.
Oh, me? I thought the viewer. I would say 7 and 3. Sounds good.
7 and 3. Okay, so 7 and 3. I'm going to split them up. Now, here's what I'm going to do. I'm going to write a number with 7 ones. So just 1, 1, 1, 1, 1, 1, 1. And I'm going to multiply it by a number with 3 ones. 1, 1, 1. And if you work it out, what you'll get is 1, 2, 3, 3, 3, 3, 3, 2, 1. Okay, next we're gonna do it again. So you can split this up however you want to.
So let's say 4 and 3.
Yeah, 4 and 3. Okay, there we go. So next we're gonna do a number with 4 ones. 1, 1, 1, 1 times 1, 1, 1. And this is going to be 1, 2, 3, 3, 2, 1. If you work it out. Next up is this one.
Yeah, you can only do
1 and 2.
1 and 2 here, right?
Yeah. So, yeah, that's the only thing you can do. 1 and 2. That one's going to be 1 times 11. That's just 11. Let's keep going. Split 4?
Let's say 3 and 1 again.
Okay. So this is 1, 1, 1 times 1, and that's 1, 1, 1. 1, 1, 1 times 1 is 1, 1, 1. Next up. Split 3?
2 and 1.
Yeah, 2 and 1. Okay. 2 and 1. You could also have done 1 and 2, but okay, you did 2 and 1. 1, 1 times 1. And that is going to be 1, 1. Okay, 1 is done. That's we can't do anything anymore. Okay, 2. Let's split 2. Okay, I'm gonna do it for you. 1 and 1. 1, 1.
Because I guess we're just basically waiting until it's only ones left, right?
Yeah. 1 times 1 is 1. Okay, next up, you can split 3.
Two and 1?
2 and 1, okay. 2 and 1. So we get 11 times 1. Wait, hang on. I'm gonna put the 1 over here to line these up nicely. This is gonna be 11. split 2? Okay, I'm gonna do it for you. 1 and 1. 1 times 1 is 1. And finally, split 2. Okay, look, it's gonna be 1 and 1, right? So we get 1 times 1 is 1. All right, now what we're gonna do is add up all of these together. Just add them. Okay, let's do it.
All of the answers.
Okay, I can't do that in my head like I did with the multiplication, unfortunately. But we're gonna do it on here. So 1, 2, 3, 3, 3, 3, 3, 2, 1. Okay, and then we're gonna add 1, 2, 3, 3, 2, 1. Add 1, 1, add 1, 1, add 1, 1, add 1, add 1, add 1, add 1 equals 1, 2, 3, 4, 5, 6, 7, 8, 9. We get 1, 2, 3, 4, 5, 6, 7, 8, 9.
So those are consecutive numbers.
Yeah, it's counting up. It's really cool. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, how did this work? Okay, so the first time I set this puzzle, I didn't know how this. I just didn't know how this works, and so yesterday I figured out how it works. Here's my proof that it works. This by the way is also gonna be just so this is also just a lesson on like problem solving tips, because and this is also going to be a proof technique called induction. So this is going to be kind of exciting. Okay. Okay, so the first thing you realize, we'll start with 10. What if we could simplify the problem? The first thing you should try when trying to solve a problem is try to simplify it. So I'm going to use the red pen from now on because the blue pen isn't working anymore. Okay, so let's start with 2. Really, really simplified down. And so we can split it up into 1 and 1. This is the only way we can do it, by the way. We can only do it based on 1 and 1. So we get 1 times 1 is 1, and we add 1 to nothing, we get 1. Okay, that's the first case done. We got the numbers counting up to 1. Kind of trivial, but yeah, there we go. Next up, 3. So we start with 3, then we're going to split them up, and there's only one way to do it. I made a big thing about they could go in either order, but no, it doesn't, the order doesn't matter, so so we can do this 2 and 1, and then I could do 1 and 1. This, again, is the only way I can do it. There's no other way I can do it for 3. So now we get 1, 1 times 1 is 1, 1, and 1 times 1 is 1. Add them together. You'll get 1, 1, add 1 is going to be 1, 2. There we go. So now we have 1, 2. Then I did 4. So that's going to be, and there are actually 2 ways you can do it. Let me write down both. You can do either split it up into 3 and 1, or you can split it up into 2 and 2. For 2, we know there's already only one way, 1 and 1. So And for 3, we also know there's only one way. There we go. So these are the 2 ways to do it. And if you start carrying out the sums, you would see that we get 1, 2, 3. So that's kind of cool. And then we started doing it for 5, and then I was like, okay, hang on. We aren't getting anywhere with this. I can't find patterns in the trees that I get. So I resorted to this fancy mathematical proof technique. Let's say that we know it's true for all of the numbers 1 up to n. So I assume it's true for all the numbers 1 up to n. Actually, no. Let's assume it's true for all the numbers 1 up to n minus 1. And we want to figure it out. It's true for n. Okay, so let's think about the first split. So we're going to start with n in little dot thingies. And we're going to split it up into 2 numbers. Let's just give them arbitrary names. Let's call them m and k. So we're splitting n up into m and k. Now m and k are, because we split it up, are smaller than n. So we know it's true for them. So if we split up n dots, so we do m, we split m up further, and if we add all of those together, then, okay, we know it's true for m, so we get 1, 2, 3, m. I split n up into m and k, and then m, we're going to split it up further, and so we're going to get, and m automatically contributes 1 to 3 in m, 1, 2, 3 to m. Because we know m is a smaller number, we already know. Because we're assuming n is the smallest number we don't know it's true for. Okay, so we're going to do the same thing for k. So k, we're going to split up again. So we're going to split it up, and that's going to contribute 1, 2, 3, and so on, up to k. And finally, the final bit that we're going to add in is the part that has to do with this split. So that's 1, 2, 3, 4, 3, 2, 1, or something like that. So this is going to be the result after multiplying m1s by k1s. This is multiply. Okay, so that plus that is going to give us the total result. Okay, so this it gives us evidence that it's going to be a fixed outcome, but it doesn't give us, but it doesn't prove that it's exactly 1, 2, 3, 4, 5, 6, 7, 8, 9. So let's do this. Let's actually do a specific example. Let's say m is 5 and k is 3. So this is a specific example. M is 5 and k is 3. That actually really helped me when I was trying to prove this. So then I started doing this. So the result for 5, where's the result for 5? Is 1, 2, 3, 4. And for 3, it's 1, 2. 1, 2. And then we're going to add the result after multiplying 5 ones by 3 ones. Now, okay, here's the trait that I used for multiplying these sorts of numbers in my head. So let's say that we want to multiply 5 ones by 3 ones. 1, 1, 1, 1, 1, times 1, 1, 1. So we have 1, 1, 1, 1, 1 times 1, 1, 1. What I do is I take 1, 1, 1 copies of this one and add it together. But here's the thing, I already know that 10 times 1, 1, 1, 1, 1 is 1, 1, 1, 1, 1, 0. So I basically just have 1, 1, 1, 1, 1, 1. And then a whole bunch of 1, 1, 1, 1, 1 zeros. But here's the thing. I already know that a 10 1, 1, 1, 1, 1 zeros is going to give us 1, 1, 1, 1, 1, 0, 0. So I can compress 10 1, 1, 1, 1, 1 zeros into 1, 1, 1, 1, 1, 0, 0. If I end up doing that, 1, 1, 1, 1, 1, 0, 0. And I'm always going to end up with this. I'm always going to end up with these like 1, 1, 1, 1, 1s shifted along like this. Shifted along. And the number of times it's shifted is the number of ones in the other number. And then if I add these together, so I'm going to do 1, 2, 3, 3, 3, 2, 1. So the eventual number that I get is going to be this. So now we can fill that in here. 1, 2, 3, 3, 3, 2, 1. 4 plus 2 plus 1 is 7. 3 plus 1 plus 2 is 6. 2 plus 3 is 5. 1 plus 3 is 4. 3, 2, 1. Okay, first of all, so why is it counting up? For this first part of the number, it's just counting up. There is only this part of the number and it's counting up. For this second part of the number, this part of the number is counting up, and this part actually stays the same. And for the third part of the number, this number is counting up, this number is counting up, and this number is counting down. So that is a net result of the result number counting up. So this number starts counting up, and then this one starts staying the same exactly when this one starts counting up from 1. So this keeps counting up the way it is, and then in this part of the number, this number starts counting down exactly when this one starts counting up. So this is why it keeps counting up seamlessly. So, okay, the grand finale. We have now proved that if we know it's true for all the numbers 1 to n minus 1, we know it's true for n. And we know it's true for 1, well, that's kind of the trivial case, and we know it's true for 2. Now, okay, it's true for 1 and 2. Okay, so that means it's true for 3. Okay, but now we know it's true for 1, 2, and 3, so it's true for 4. Okay, but now it's true for 1, 2, 3, and 4, so we know it's true for 5. And now we know it's true for 1, 2, 3, 4, and 5, and now it's true for 6. And so on, all the way up until 10. And that's why we know it's true for 10, that if we split them up, break them down as products, and then we get 1, 2, 3, 4, 5, 6, 7, 8, 9. Always.
QED.
So this is actually quite a good method. Start simple, then work your way up, and then there's this is also a proof technique called induction. In particular, strong induction. This is also just a great puzzle. So I hope you liked it, and see you next time. I'll see you. Bye. Are you actually gonna put this in the video?
Maybe.
I mean, it would be funny to, like, at the end of the video have, like, that sentence, like, are you gonna put this in the video? Yeah!